All right, good evening. Welcome back to Calculus 2. Today we are going to talk about integrating rational functions. And the first thing you might be tempted to do, and this is not a bad plan, is see if you could figure out a u and then figure out a du and see if it'll actually fit. So we have u is equal to x squared plus x minus 2, du equals 2x plus 1. And that's kind of going to be a hard thing to hammer into the shape of a 5x plus 7. So sometimes you can do this, and sometimes it takes a little bit more hammering than you would think. And other times we're going to do something called partial fraction decomposition. Okay. So the idea with partial fraction decomposition is that we're going to factor the bottom of this function here. So we can say this is 5x plus 7 divided by, what do we have here? We have x plus 1, and I think, no, x minus 1. Yeah, x minus 1. There we go. Let's go ahead and put that in there properly. So we have x minus 1, x plus 2. So what we're going to do is we're going to assume that this fraction was turned into something that was some a over x plus 1 plus some b over x plus 2. Now, there are some rules to how you figure out partial fraction decomposition. For linear terms, that's an ax plus b, in this case, x minus 1, we're going to assume there's a constant over the ax plus b. And then for as many as you need. Okay, so if I had three terms, we would have a C over, the next one plus a D over the next one, dot, dot, dot. Sometimes we're going to have what they call repeated measures. You might have an x plus 1 squared. We'll see stuff. What we would do is we would say there's an x over x, a over x plus 1 plus a b over an x plus 1 squared. For as many repeated measures you're going to have, this still counts as a linear term. Okay. So when you get up a little bit bigger, you're going to have one that's like maybe you have some stuff over an ax squared plus bx plus c, where you can't factor this. This is called an irreducible quadratic. Okay, so irreducible quadratic. Okay. And when we have an irreducible quadratic, we're going to assume the top looks like an ax plus b over said irreducible quadratic. Okay. So we'll have, we'll do an x plus 1. Actually, let's do an actual proper example. So let's see. What if we have a 7x plus 2 over, and let's do it with an x squared plus 9 times an x minus 1. All right, so we're going to divide this out into a partial fraction. So we're going to say we have an ax plus b because x squared plus 9, it's missing a middle term, but I can't factor that, right? That's an irreducible quadratic. So I'm just kind of stuck with x squared plus 9 on the bottom there. So you'll factor it. Plus a c over x minus 1. And what we're going to do is we're going to set this up as a system of linear equations in order to figure out what a, b, and c are in order to integrate this thing more properly. Okay, so regardless of what we come up with as far as our ax, a, b, we're going to go ahead and figure out what has to happen here. We'll set our u to be x squared plus 9, or du will be ax plus b. Okay, so that's the idea is we're going to use these partial fraction decompositions to make things that are kind of hard to integrate into terms that are much easier to integrate. Because if this turned into an a over x minus 1 plus a b over an x minus 2, I can integrate those two things in my sleep. Sometimes I have. This isn't going to be too much of a problem. Okay, so let's go back to the problem we were talking about. And we will do some harder and more involved examples as we go through this. So when you have when you have linear terms, we're going to assume that we have a constant over linear term. You have an irreducible quadratic, we're going to assume we have a linear function or a linear piece over a quadratic. Okay. If we have repeated terms, then we don't change this. This didn't turn into a bx plus c. Just because there's a squared under here, it's not an irreducible quadratic. So we keep it as a constant function over a linear squared term because it's kind of a special rule where you have a repeated measure. Okay, it gets kind of tricky when you have a reducible quadratic squared and you have to do repeated terms with irreducible quadratics. You end up with a bit of a mess, but it actually breaks down to something that's rather nice. Okay. Um, the only thing you really have to worry about is notice that all of the examples that I kind of showed you, that the degree of the numerator was one less than the degree of the denominator. If it's not smaller than, right? Going back to third grade when you were learning fractions, if you had a problem, if you had an answer like 7/9, Sister Mary Agony would say, job well done. You have a good fraction there. I'm pretty happy. If you ended up with a 16/9, i.e., the top was bigger than the bottom, Sister Mary Agnew would say, no, 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 no. That is not the right answer. You better fix it before I go get my ruler. Okay. So we say, oh, we got to fix that. So we're going to say, okay, 16 minus 9 is going to be 7. So this would be 1 and 7/9 and work through it that way. So we'd have this mixed fraction here. Same thing with polynomials, except you need degrees rather than actual values. So we're not looking for values, we're looking for degrees. So if you have some kind of x squared over an x, we have to do everybody's favorite thing in the world, which is polynomial long division. We will definitely do some of those with this video series, but we're not going to start off with this. But I just want you to be aware that the top has to be smaller in degree than the denominator. Okay, the top has to be smaller than the bottom. It has to look like what elementary school kids would call a proper fraction. It's just that we're looking at the degree, not the number. All right, so just be careful about that. Don't let Sister Mary Agnew catch you. Okay, just it hurts. Okay, so here we go. We have a 5x plus 7 divided by, so let's just take it from the top. We have a 5x plus 7 divided by, and here we have an x minus 1, x plus 2. Okay, x minus 1, x plus 2. Now, we're going to divide this in half. We're going to do partial fraction decomposition. Okay, so I'm just going to put a little topics in there because we're going to make it's kind of like a new heading for a paper. So we're just going to kind of set that off to let people know what we're doing. Plus a b over an x plus 2. And we're going to say this equals a 5x plus 7 divided by some denominator. I'm just going to call the denominator d, and that's this whole thing that we have sitting right here, okay? Now, we have what's called a rational equation. The first thing that we're going to deal with a rational equation is to make it not a rational equation. That's how you solve these things. So what I'm going to do is I'm going to multiply by x minus 1, x plus 2 to both sides. What's that going to do to my right-hand side? Well, I'm just going to have 5x plus 7 on my right-hand side here. Okay, now, if I make this whole grouping here, visit each of these pieces here, in the first piece, the x minus 1's cancel, so we have an a times x plus 2. Okay, plus b, now here, that's x plus 2's term. X plus 2's cancel, so we have a b x minus 1. Okay, let me go ahead and multiply this out. So we have an ax plus 2a plus bx minus b is equal to 5x plus 7. Fantastic. Now, what I'm going to show you for this one is we're going to say, let's go ahead and equate the coefficients. There's another way I'm going to do this. So you'll get to the end and you'll say, oh, I need the other way. So we're going to do equate the coefficients. Okay. Now, when I'm equating the coefficients, that goes with saying that the stuff, the x stuff, the stuff that's coefficients for the x stuffs on the left should equal to the x stuff on the right. So x's plus x's should equal to x's. Constants plus constants should equal a constant. So I'm going to say, okay, here's my x row. So I've got an a plus a b must be equal to 5. For my constant function, we're going to have a 2a minus b must be equal to 7. I'm just taking what the constants are. There was 2 a's, there was a b. There's no x's in this term at all. Here we have a system of equations, 2 equations, 2 unknowns. This is probably the easiest system of equations that anybody has ever posed to you. So that's good. We're starting off at a nice, easy footing here. So what I'm going to do is I'm just simply going to add these 2 equations together. So we're going to have a plus 2a to be 3a. Oh, would you look at this? B minus b, we get no b's left, is equal to 5 and 7 make 12. So a must be 12 over 3. A equals 12 over 3, which is 4. We could plug this back into the original equation. We could say, okay, 4 plus b must be equal to 5. Hence, b is equal to 1. Okay, so as I go to my partial fractions, what we're going to do here is we're going to say we have an a, which is over the x minus 1s. Be careful to keep them all straight this way. So we have a was equal to 4. So we have 4 over x minus 1. So what we have to integrate is 4 over x minus 1 plus b 1 over x plus 3. All right, that's not too bad. Or x plus 2, rather. I don't know where the 3 came from, but x plus 2. We'll go ahead and change this. There we go, x plus 2. Okay, and this was equal to this 5x plus 7 divided by, and we're still integrating, x plus 2, x minus 1. Again, I couldn't integrate this thing to begin with, but these pieces, because the linearity of the integral sign is that we can do integral is going to go to both of these pieces. So this is just going to be the integral of 4. So we have 4 integral of 1 over x minus 1 plus 1 integral 1 over x plus 2. You don't need to do that step. That's okay. Both of these have a dx equals the original integral. Okay. And we're just going to integrate this. So this is going to be 4 natural log of, don't forget the absolute value, x minus 1, plus natural log of x plus 2, plus c, because it's an indefinite integral, and that's going to be my answer for how this thing is done. So let me jump back to before I set up, I have my equate the coefficients. I'm going to show you one other method here. So I'm just going to repeat this number right here. So we have a times x plus 2. Okay, so let me just go down here. So we have a x plus 2 plus b, and I think we had an x minus 1, and this was equal to 5x plus 7. So the first thing I did was I created a system of equations, and then I solved them, and that's how I did it. This is a little bit of a shortcut, which works really well when you have linear equations. It doesn't work so much when you have repeated measures. So I want you to know how to do both of them, but as you're doing your homework, pick whichever way is the fastest way for you. But here we're going to say set x equal to 1. Well, if I set x equal to 1, we're going to have a times 1 plus 2 is 3. What happened to my b's? They all went away. This is called the cover method, okay? So that's what this thing is called. Because pretty much, if you were doing this on a piece of paper, I would pretty much put my thumb over this bx plus 1 and cover it, because that whole term goes away, equals, now what did we set x to? X was 1. So we have 5 plus 7, 3a must be equal to 12. A is equal to 4. This is a very nice little shortcut. That's a nice way to do this. I don't really care how you do it, just that you can do it. I will say that relying too much on the cover method, and then you end up with having, because maybe you have repeated terms, and you absolutely have to use the system of equations, you should practice it at least a little bit. If you plan on taking linear algebra, you should practice it a lot, okay? Because it's a system of equations, you should be better at doing this. Okay, in order to finish this off, well, we set x equal to 1. Let's go ahead and set x equal to minus 2. So we go ahead and plug in, we're going back to this equation up here. Here's my original. When I set x equal to negative 2, well, this whole piece goes away. And here I have negative 2 minus 1. You're $2 in debt, you spend one more dollar, negative $3 in debt. So we have negative 3b equals, and then here we have x was equal to minus 2. So I have 5 times minus 2 plus 7. So we're going to end up with negative 10 plus 7, negative 3b equals. So negative 3b equals negative 3. Oh, b must be equal to 1. Isn't that what we had before? Right? We had 4 for my a. That was going to be over the x minus 1. And we had 1 over the x plus 2s. We get the same answer. This was just a little bit faster. Again, you can use whatever method you please. When I took Calculus 2, I didn't like the shortcut. It kind of bothered me. It's like, So I just did it with systems of equations the whole time. And at the time, I was taking linear algebra, so setting it up as a system of equations, we used matrices, felt like the natural thing for me to do. So that's just what I felt comfortable with. You can use the cover method. Most students prefer to use the cover methods. But once you get used to it, it's a much faster way to go. So I encourage you to go ahead and do that. But you don't have to. like I said, me personally, I was learning linear algebra, so at the time I like setting up the systems of equations. It just felt better. It took me a little bit longer, but it felt better for me to do it this way. So that's how I did it. So that's how we're going to go ahead and solve these kinds of problems. We're going to do a lot more examples just to kind of show you how this thing works. But I think you've listened to me enough. So I'm going to stop the video here and say thank you very much for watching. I will see you in the next one, and take care.